On July 1st, 2025, something extraordinary slipped into our solar system, and for the first time in human history, we had advance warning. A faint speck of light, barely noticeable against the vast backdrop of stars, triggered an alarm that would reshape our understanding of what comets truly are. The Atlas survey in rewrote, Chile, caught the first glimpse of an object that didn't belong. It was moving too fast. It was coming from too far away, and it was heading toward a rendezvous with the sun that would reveal secrets locked in cosmic ice for billions of years. This wasn't speculation. This wasn't a theory waiting to be verified. Within hours, the measurements submitted to the Minor Planet Center returned a result that sent shockwaves through the astronomical community. The object's orbit was hyperbolic. After accounting for every conceivable gravitational influence in the solar system, the trajectory refused to close. The comet wasn't trapped in our cosmic neighborhood. It was passing through on a one-way ticket from the stars. The discovery of 3I/Atlas marks a watershed moment. This is the third confirmed interstellar object in history, but it's the first to be caught early enough for a comprehensive scientific investigation. Where the previous visitors slipped away shrouded in mystery, Atlas arrived with time to spare. Time for telescopes around the world to gather data. Time for scientists to piece together a portrait of a world billions of years older than our own. Time to ask questions that should have remained forever unanswered. But here's where the story becomes truly strange. The more we learned about 3I Atlas, the less it fit our expectations. The hype predicted an alien artifact, a probe, perhaps even evidence of engineering from another civilization. The data revealed something far more alien than any human invention. A comet following rules we didn't know existed, composed of materials we'd never seen before, and carrying chemical fingerprints from a stellar system older than memory. The real knowledge about 3I Atlas is stranger and more uncertain than the headlines suggested. And that story, the true story, the science story, is far more compelling than fiction.
When astronomers talk about velocity, they speak in terms that matter only when you're dealing with the infinite. But the number that defined 3I Atlas in those first crucial hours was devastatingly simple. 58 kilometers per second relative to the sun. That's nearly twice the escape velocity from our solar system at the comet's current distance. No object born from the dust and gas that formed our planetary system can achieve that velocity on its own. No gravitational kick from Jupiter, no collision, no chain of events within our stellar neighborhood can explain it. The only way to move that fast is to start from somewhere else entirely. The hyperbolic orbit told the real story. Imagine the solar system as a well, and everything inside it as objects trapped by the gravity of the sun. They can orbit forever, settling into elliptical paths that bring them back to the same place year after year, century after century. But a hyperbolic orbit is different. It's the trajectory of something that has climbed out of the well with enough energy that it will never be recaptured. It will round the sun once, and once only, before vanishing into the interstellar dark from which it came. Pre-discovery images pushed the timeline backward. Other Atlas telescopes had captured the comet in June. The Caltech Zwicky Transient Facility had caught it even earlier. Each new data point tightened the orbital solution until, by July 2nd, the Minor Planet Center issued the formal designation, 3I, the third interstellar object. The confirmation came not from theory or speculation, but from hard evidence, the kind of evidence that doesn't allow for doubt. But confirmation of origin was only the beginning. When astronomers traced the orbit backward, far beyond the outer planets to the empty space between the stars, they found no solar system source, no known comet family, no ancient collision debris, nothing that could have been flung from our neighborhood. Based on the comet's velocity and its likely journey through the galaxy, models suggest 3I Atlas could be anywhere from 3 to 11 billion years old. That means this visitor may have formed before our solar system finished assembling its planets, before the Earth itself solidified, before complex chemistry was even possible on this world. An emissary from deep time had arrived, and it was carrying secrets. Long before official discovery, 3I Atlas had already begun to announce itself to the universe. The Transiting Exoplanet Survey Satellite, TESS, orbits Earth, collecting full-frame images for its own scientific mission. But those deep exposures also caught something unexpected. A faint signature of increasing brightness in the region where 3I Atlas was quietly drifting inward from the outer darkness. In May and June of 2025, astronomers combing through archived test data found evidence that the comet had been brightening steadily over several weeks. This wasn't a sudden, dramatic flare. This was a gentle but unmistakable rise in luminosity, the signature of a nucleus already beginning to shed gas and dust under the distant warmth of our sun. The magnitude hovered around 20, then crept toward 19.3 as June ended. For a cold, distant body orbiting at nearly 4.5 astronomical units from the sun, that level of brightness suggested something remarkable: activity. Not a silent, inert rock drifting through space, but a dynamic world responding to the approaching heat. The significance of this early activity cannot be overstated. If a comet begins brightening far from the sun, it means its surface is layered with volatile ices that sublimate at low temperatures. Carbon dioxide, carbon monoxide, perhaps exotic volatiles never cataloged in detail before. These are the building blocks of unpredictability, the ingredients that make comets volatile and difficult to model. They're the signature of a world shaped by conditions radically different from those that formed the icy bodies of our own solar system. The light curve, the graph of how brightness changed over time, revealed no obvious periodic flicker, no clear sign of a spinning nucleus. If there was a rotation period, it remained hidden beneath the glare of the coma, obscured by the dust and gas already pouring from the surface. Later, ground-based observations would hint at a possible rotation period of 16 hours, but those early survey data offered no confirmation. What they did provide was context and urgency. 3I Atlas was not a faint, inert speck. It was active, volatile, rich, and already building a visible coma before the world even knew it existed. The early light curves pushed astronomers to act with unprecedented speed. Every major telescope with the capability to track faint, fast-moving objects began jockeying for observing time. The window for studying an extraterrestrial visitor this early, with this much warning, had never opened before. Every hour counted. The hunt was on to turn that faint, steady rise in brightness into real scientific insight about what makes an interstellar comet tick.
On July 21st, 2025, the Hubble Space Telescope locked onto 3I Atlas for a rare, high-stakes imaging session. The comet was already racing through the solar system at nearly 60 kilometers per second. And even Hubble's precision optics had to compensate for that extraordinary speed. The resulting images showed background stars stretched into thin streaks, silent witnesses to just how fast this interstellar visitor was moving across the sky. But the background stars were merely the backdrop to a more important discovery. At the center of the expanding coma, astronomers found the first hard constraints on the nucleus itself. Early estimates had been wildly speculative. Some researchers, eager to explain unusual brightness, had proposed a nucleus as large as 10 kilometers across, rivaling the biggest comets in our solar system. Others wondered if the size estimates might hint at something even more exotic, something engineered perhaps. Something that defied conventional explanation. Hubble's high-resolution images cut through speculation and delivered precision. Using careful photometry, subtracting the light from the surrounding dust, the Hubble team
narrowed the possible diameter between 0.44 and 5.6 kilometers, with most analyses pointing firmly toward the lower end of that range. The nucleus of 3I Atlas is smaller than Manhattan. It's small enough to fit inside a large city, yet massive enough on a human scale to be incomprehensible. This constraint was more than a technical detail. It was a fundamental shift in understanding. The size of a comet's nucleus determines almost everything about its behavior. A larger nucleus can store more volatile ices, driving more intense outbursts and surviving closer approaches to the sun. A smaller one becomes fragile, vulnerable to fragmentation, potentially disintegrating under intense solar heating. For 3I Atlas, the new constraints meant that many of the more speculative early theories, giant spacecraft, planetary shards, disguised asteroids, no longer fit the evidence. The object is simply too small to be anything but a comet's nucleus, covered in volatile ices and wrapped in a shroud of dust. The Hubble team, led by David Jewett at UCLA, had relied on techniques honed over decades of comet studies. By imaging through multiple filters and comparing the brightness profile of the inner coma to theoretical models of dust scattering, they could tease out the faint signal of the nucleus itself from the surrounding haze. The process is never perfect. At these distances, even Hubble cannot truly resolve the nucleus from the surrounding material. But the combination of high angular resolution and careful mathematical modeling gave the best shot yet at determining the comet's true size. Knowing the nucleus size allowed astronomers to estimate how much material the comet was losing as it heated up, and more importantly, to compare that loss rate with comets born in our own solar system. The dust production rates inferred from Hubble's images turned out to be surprisingly ordinary. By this metric, 3I Atlas looked less like an alien artifact and more like a product of natural processes shaped by billions of years adrift between the stars. But the images left one critical question unresolved. While the size of the nucleus was now constrained, its composition remained a mystery. The images showed a sunward plume of dust, hinting at active jets or localized outgassing, but offered no chemical information. For that, astronomers would need to turn to spectroscopic instruments, devices capable of splitting the comet's light into the chemical fingerprints that would reveal its true nature.
In early August 2025, the James Webb Space Telescope, humanity's most advanced eye on the cosmos, turned its gaze toward 3I Atlas. On August 6th, the NIR SPEC instrument captured the comet's infrared signature, splitting the coma's faint glow into a barcode of chemical fingerprints. What it found was not the usual story that astronomers had come to expect from decades of studying comets. Most comets in our solar system wake up when water ice begins to sublimate, turning directly from solid to gas as sunlight heats the nucleus. That transition is what drives the classic outgassing jets and the characteristic dust plumes that make comets visible to the naked eye. Water is the primary architect of a comet's activity profile, the fundamental fuel that shapes its behavior as it approaches the sun. It's the central character in the story of how comets work. But 3I Atlas wasn't playing by those rules. The spectral data revealed something shocking. Carbon dioxide and carbon monoxide were dominating the gas output. At this distance from the sun, where water should be the primary driver of activity, it was instead a minor player. CO and CO2 accounted for the vast majority of the escaping gases, while water vapor, normally the star of the show, was barely detectable. This was an alien chemistry. In solar system comets, carbon dioxide and carbon monoxide only take center stage when a comet is far from the sun, so cold that the more volatile ices remain frozen while only the most easily sublimated materials escape to space. But 3I Atlas had already built a thick, active coma, powered almost entirely by these exotic ices, while still in the cool outer solar system where water should dominate. It was as if the comet were following a script written by a different star, in a colder world that never existed in our cosmic neighborhood. The physics behind this chemistry is revealing. Carbon dioxide is a molecule that needs far less heat to escape than water ice. It begins to sublimate at much lower temperatures, meaning a comet can kick off its activity while still far from the sun. For 3I Atlas, this early activity wasn't just a gentle simmer. It was a raging furnace powered by molecules that shouldn't be active at all at this distance. The JWST data showed that the amount of gas pouring from the surface was enough to drag dust grains along with it, launching them into space and building up the coma visible from Earth. But there was a twist, a detail that revealed something even stranger about this visitor from the stars. The dust wasn't behaving like it should. Instead of drifting gently away in a classic tail, much of it was being blown sunward, back toward the light, as if the normal rules of radiation pressure had been inverted. That wasn't just an oddity, it was a crucial clue. The sunward dust plume likely meant the grains were being launched by sudden bursts of gas, perhaps from pockets of CO2-rich ice close to the surface. When these pockets ruptured, they acted like tiny geysers, blasting dust outward with enough force to overcome the gentle push of sunlight. The result was a coma that wasn't just bright, but oddly structured, with a striking sunward spike of dust that stood out against the usual cometary haze. This kind of activity hinted at a nucleus with a patchwork landscape of volatile ices buried at different depths, exposed by cracks and fractures. It was a pattern that matched some of the most active comets
humanity had ever observed, but the chemistry was all wrong for a solar system native. The balance of CO, CO2, and water vapor pointed to a formation environment much colder than the region where our own comets formed. A protoplanetary disk around a different star, shaped by conditions we can only theorize about. In other words, 3I Atlas was carrying a chemical memory of another world, frozen in place for billions of years, now thawing for the first and only time as it raced past our sun. It was a message from the stars, written in molecules, speaking of worlds we would never see.
In late August, Gemini South, equipped with the GMO optical spectrograph, turned its attention to 3I Borisov Atlas and captured a slender tail stretching roughly 1.2 degrees from the nucleus. For an interstellar object, even a faint tail is a clear signal that the nucleus is shedding dust and gas, driven by the combined effects of sunlight and the solar wind. This visible outflow marked the comet as undeniably active, not just a frozen relic drifting through space. But the Gemini team's real discovery emerged in the spectral data. A distinct emission line from CN, cyanogen, a molecule of carbon and nitrogen, stood out against the background. CN is a classic indicator of cometary activity, a molecule that glows as sunlight breaks apart more complex organic compounds in the coma. In most solar system comets, CN is joined by C2, diatomic carbon, and the ratio between them serves as a kind of chemical fingerprint unique to each comet. Here, C2 was almost absent. The C2 to CN ratio measured less than 0.09, a level that places 3I Borisov Atlas firmly in the category of carbon-chained depleted comets. This wasn't just a curiosity or a minor deviation from expected values. It was a profound anomaly. In our solar system, comets with such low C2 to CN ratios are rare, and those that do exist typically originate from the coldest, most distant regions of the outer solar system, the far reaches of the Oort cloud, where temperatures barely rise above absolute zero. For an interstellar visitor, this chemical depletion hints at a formation far from its parent star, in the frozen outer regions of an alien protoplanetary disk, or perhaps a long exposure to cosmic rays during its billions of years of travel between the stars. Cosmic rays are known to damage complex organic molecules, breaking apart the carbon chains that produce diatomic carbon. Over billions of years, wandering through the harsh radiation environment of interstellar space, even robust molecules can be degraded, transformed, remade by processes we're only beginning to understand. The Gemini spectra, collected on August 27th, captured the comet's activity intensifying as it drew to 3 astronomical units from the sun. The presence of gas and dust was unmistakable, but the chemistry was unlike anything seen in most homegrown comets. As the tail extended and the CN emission strengthened, astronomers gained their first quantitative look at the physical processes shaping this extraordinary visitor. Dust grains carried by escaping gas traced the comet's path, while the lack of C2 set it apart from nearly every other comet on record, raising questions about conditions in worlds we would never see. These findings didn't just add to the catalog of known comets. They redrawn the boundaries of comet science and opened new questions about the dust itself, questions that would soon take center stage in an entirely unexpected way. In the summer of 2025, 3 polarimetry teams positioned their instruments with laser focus on 3I Atlas. At the Very Large Telescope in Chile, the Nordic Optical Telescope in Spain, and at Rojan Observatory in Bulgaria, observers measured how sunlight scattered off the comet's dust. What they discovered was a light-scattering signature that defied every known pattern in cometary science. When sunlight bounces off comet dust, it becomes polarized, the electromagnetic waves oscillating in a preferred direction rather than randomly. The degree and direction of this polarization shifts as the angle between the Sun, comet, and Earth changes, a relationship that astronomers call the phase angle. Over decades of comet studies, scientists have developed detailed models of how dust should behave. Most comets show a modest dip into negative polarization at small phase angles, then a steady climb into positive territory as the phase angle increases. It's a predictable pattern, well understood and documented. 3I Atlas broke that mold entirely. Its minimum polarization plunged to negative 2.77% at just 6.41 degrees, a value twice as deep as the most extreme comets in the solar system, and confined to a much narrower range of angles. The inversion, where polarization flips from negative to positive, came at 17.05 degrees. The slope of the negative branch, how quickly polarization drops with angle, was a sharp negative 0.40% per degree. For context, even the dustiest comets like Hale-Bopp or Borisov bottomed out at -1 to -1.5% and over a much broader phase angle range. Such a deep, narrow branch is more than an oddity. It's a fingerprint of dust's microphysics, a signature of something fundamentally different about the material being shed from 3I Atlas. The numbers point to dust grains that are large, dark, and likely rich in ices or complex organic compounds. The steep slope suggests high porosity dust, fluffy, loosely bound aggregates, rare in the inner solar system. The low inversion angle, just over 17 degrees, is more typical of some rare asteroids and trans-Neptunian objects, but even those don't reach this depth of negative polarization. Modeling these curves requires advanced light-scattering simulations, computational work of extraordinary complexity. Only a narrow set of parameters can reproduce such extremes. The most plausible scenario involves dust aggregates with a mix of ices and dark organics held together in a fragile, highly porous structure. Polarimetry maps showed little variation across the coma, hinting at a global process shaping the dust, not localized jets or regional variations, but a planet-wide transformation of the comet's surface material. No comet or asteroid in our solar system has shown a polarization curve like this. Even 1I Oumuamua, the first interstellar visitor, showed far different scattering properties. 2I Borisov, the second confirmed interstellar object, had a much shallower negative branch. But 3I Atlas stands apart, a new class of object,
dust shaped by conditions colder and older than anything in the solar system. Born in the dark between the stars in an environment that left its mark on every grain.
On September 7th and 8th, as a total lunar eclipse drew eyes skyward, a quieter but equally important pursuit played out in backyards and small observatories across the world. Amateur astronomers, equipped with everything from modest DSLR cameras to more advanced imaging systems, focused their optics on a faint object drifting near the moon's shadow. 3I Atlas, the interstellar comet already stirring debate among professionals, became the subject of a grassroots observation campaign. Their images, shared in real time across online forums and social media, quickly sparked a new controversy. Several observers reported seeing a distinct green hue in the comet's coma, a green glow that, in cometary tradition, often signals the presence of diatomic carbon fluorescing under sunlight. It's a phenomenon well known to comet watchers, a telltale sign that a comet's coma is rich in carbon chain molecules. Bright green means active carbon chemistry. No green means those molecules are depleted. It's a simple visual indicator of complex organic processes. But this time the story was complicated. Earlier spectroscopic studies by the Gemini and VLT teams had found 3I Atlas to be almost barren of carbon chain molecules. The expected C2 signature, the usual culprit behind a comet's green glow, was missing or vanishingly faint. The C2/CN ratio was the lowest of almost any comet ever recorded. Yet online, raw and stacked images from amateur observers seemed to show green unmistakably. The question arose in forums and discussion threads. Was this a real feature or a trick of the camera? Some argued the answer lay in the technology itself. Digital sensors, especially when operating under the odd lighting conditions of a lunar eclipse, can exaggerate colors or introduce artifacts that mimic features that don't actually exist. The moon's coppery light, filtered through Earth's atmosphere and further scattered by dust and water vapor, created a challenging environment. The changing sky brightness, the reflection off the moon, the challenge of imaging a faint object against such a dynamic, unusual backdrop, all of these factors conspire to distort subtle hues and introduce systematic errors into color imaging. Without standardized calibration, without reference stars for comparison, without controlled settings, these amateur images remain suggestive rather than definitive. They were hints, possibilities, intriguing data points that demanded further investigation but couldn't stand alone as scientific evidence. No professional observatory reported a green emission spike on those nights. No peer-reviewed photometric analysis confirmed the amateur claims. The green hue remained unverified, a tantalizing mystery waiting alongside other unanswered questions, a possibility tantalizing enough to mention, but uncertain enough to question. This episode captures both the promise and the profound limitations of citizen science. Amateur astronomers extend the reach of discovery, catching fleeting moments that might otherwise slip past. But the absence of rigorous calibration, controlled conditions, and standardized methodology means even the most striking images demand skepticism. The lunar eclipse, while dramatically beautiful, created a challenging environment for accurate color measurement, one of the worst possible conditions for precision photometry. For now, the green hue of 3I Atlas remains unverified. It waits alongside other unanswered questions, a possibility tantalizing enough to mention, but uncertain enough to question. The lesson for astronomy is clear. Seeing something new is only the beginning. What matters is proving it with evidence that stands up to scrutiny, no matter how compelling the first glimpse may be. Science demands rigor.
It demands evidence. It demands that we question even our own observations when they contradict more careful measurements.
Avi Loeb's name surfaces often when interstellar objects make headlines, and 3I/Atlas proved no exception to that pattern. In the early days following discovery, Loeb and a handful of others proposed that the comet's path and possible size could hint at something extraordinary, perhaps something engineered, maybe even a probe sent from a distant civilization. Their arguments leaned heavily on those first rough estimates that placed the nucleus at up to 10 kilometers across. If true, that would make Atlas unusually massive for its overall brightness, opening the door, or so the argument went, to exotic explanations beyond conventional cometary physics. A 10-kilometer nucleus would be indeed strange. It would produce more dust than the brightness measurements suggested. It would be denser than typical comets. It would demand new physics, new models, new ways of thinking about how objects from the interstellar medium behave in our solar system. The scale was large enough, the anomalies prominent enough, that the hypothesis of artificial origin seemed at least worth considering. And in the early days, when data was sparse and uncertainty was high, such speculation occupied the headlines. But the story didn't stop with those first numbers. It never does. As soon as Hubble's high-resolution images came in, the size estimates dropped sharply. The nucleus was now constrained to somewhere between 0.44 and 5.6 kilometers, with most analyses pointing firmly to the lower end of that range. That's not just a technicality or a minor refinement of earlier measurements. It's a fundamental change in the object's properties. A nucleus smaller than expected means less surface area, less mass, less thermal inertia, less capacity to power the observed activity through mechanisms that don't fit natural models. More importantly, a smaller nucleus means the dust and gas production rates that once seemed anomalous now line up perfectly with what's expected from a naturally active comet subjected to increasing solar heating. The activity that had seemed excessive, requiring exotic explanations, now makes perfect sense in terms of conventional cometary physics. Each new piece of data tightened the fit between observation and natural models. The velocities that seemed unusual were revealed to be within the range for objects flung by giant planets' gravity. The spectral features that seemed strange fit naturally into a narrative of extreme formation conditions, but nothing more exotic than stellar physics. This wasn't a story about shutting down wild ideas or suppressing creativity in scientific thought. It was a case study in how science actually works when the stakes are high and the data are new. The earliest hypotheses, no matter how extraordinary, are always provisional. They're starting points, not conclusions. As measurements improve and data accumulate, models get updated, refined, sometimes overturned entirely. Some possibilities fall away because the evidence doesn't support them. Others persist because the data continues to suggest they might be worth investigating further. In the end, the weight of evidence decides what remains on the table. 3I/Atlas reminds us that discovery is often messy, that the scientific process involves false starts and dead ends and wild speculation giving way to careful measurement. But it also reminds us that the best answers come from letting the data lead, from following the evidence wherever it goes, from adjusting our theories to match reality rather than adjusting reality to match our theories.
Only 3 confirmed interstellar objects have crossed our solar system in less than a decade, but each has left a radically different impression, written entirely different rules for what we thought we knew about visitors from the stars. The first was 1I Oumuamua, arriving in 2017. It came in fast, tumbling end over end in a chaotic spin, and never showed the slightest hint of a coma or tail. No gas, no dust, nothing to mark it as a comet. Instead, it reflected sunlight with a reddish hue and changed speed in ways that defied easy explanation. It accelerated in patterns that seemed to require an invisible push, a force that shouldn't exist at its great distance from the sun. Theories ranged from hydrogen icebergs to alien light sails to outgassing from a dark surface. But the truth is that Oumuamua slipped away before anyone could pin down its nature. It remains a riddle, a dry, elongated sliver that never behaved like any asteroid or comet we've seen, taking its secrets back to the interstellar dark from which it came. Then came 2I Borisov in 2019, and the story flipped entirely. Borisov looked and acted like a textbook comet from the moment it was spotted. It grew a bright coma, sprouted a classic dust tail, and released familiar gases as it approached the sun. Spectra showed water vapor, cyanide, and carbon monoxide, nothing out of the ordinary for a comet, except that its orbit traced back unmistakably to the void between the stars. Borisov was in every measurable way a cousin to the icy wanderers of our own Oort cloud. If you had swapped its nameplate, you would never have guessed it came from another solar system. It was comfortingly normal, following the rules we thought we understood, behaving exactly as natural processes should make it behave. Now 3I Atlas lands between these extremes, occupying a territory all its own on the spectrum of interstellar possibilities. Unlike Oumuamua, Atlas is undeniably active, with a visible coma and a growing tail. But unlike Borisov, its chemistry doesn't fit our template. The gases escaping from Atlas are dominated by carbon dioxide, not water. Its dust grains scatter light in patterns that no other comet or asteroid has matched. Where Borisov felt familiar, like a comet that had simply taken the wrong exit on the highway through the stars, Atlas feels foreign, alien, not just in origin, but in every measurable trait. It follows its own rules, speaks a chemical language we're still learning to interpret, and challenges our fundamental assumptions about what comets can be. With only 3 examples, the taxonomy of interstellar objects is just beginning to take shape, but each new arrival rewrites the boundaries of what we expect from the worlds beyond our sun. The spectrum now runs from the dry, tumbling mystery of Oumuamua to the textbook activity of Borisov to the volatile, rich, chemically bizarre 3I Atlas. As future interstellar visitors arrive, and they will arrive because the universe is full of such wanderers, we'll add more data points, refine our models, deepen our understanding of just how diverse the galaxy's debris field truly is.
October 30th is circled on every astronomer's calendar with a mixture of anticipation and anxiety. That's when 3I Atlas will swing through perihelion, its closest point to the sun, at a distance of about 1.4 astronomical units. But the timing comes with a profound catch that creates a blackout of absolutely critical observations. For weeks around perihelion, the comet will vanish into the glare of the sun as seen from Earth. Ground-based telescopes, even the most powerful, will become effectively blind, forced to wait while the most intense phase of activity plays out behind a wall of daylight that cuts off all observation. This blackout isn't just an inconvenience, it's a test, a trial by fire that will determine whether everything we've learned about this visitor from the stars means anything at all. The period around perihelion is when comets are most likely to fragment, to flare, to reveal new chemistry as solar heating reaches its peak. For 3I Atlas, a body shaped by another star, a nucleus adapted to the cold darkness of interstellar space, the outcome is impossible to predict with confidence. Will it survive intact, emerging from the solar furnace unchanged, or will it break apart under the stress of extreme heating? Will the coma thicken as more ices sublimate, or will it fade as volatiles are exhausted? Will new spectral features emerge, revealing chemistry hidden until now? Will unexpected outbursts occur? Every scenario is on the table, but none can be confirmed without eyes on the target. That's where the next generation of space-based observations comes in, where planning and preparation meet reality. While Earth-based telescopes wait for the glare to subside, missions already positioned in space are ready for the critical window. SOHO, parked at the Lagrange point between Earth and Sun, is positioned perfectly to keep watch as the comet rounds the Sun. Sphere-X, with its all-sky infrared scans, will hunt for changes in the comet's dust and gas output. A distributed sensing system that can track the object even when ground observers are blinded. MAVEN, orbiting Mars, has already logged a close pass and stands ready to catch any outbursts as Atlas rounds the Sun. And the big guns, Hubble, JWST, Gemini, are queued up to resume observations the moment the comet reappears in early December. This is the critical window. If Atlas survives the perihelion passage intact, the post-perihelion phase will offer the cleanest look yet at its nucleus, now potentially altered by solar heating. The coma will be revealed, evolving, transformed by the intense energy released by the sun. Any surprises that solar heating might trigger will be captured and analyzed. The next round of data will decide which theories hold up and which fall away. Will determine whether our models of cometary behavior need refinement or radical revision. For now, the astronomical community waits, watching the horizon, preparing instruments, calibrating detectors, making sure that nothing will be missed when the moment comes. Scanning the horizon for the first sign of a returning traveler and the answers it may finally bring.
3I Atlas stands now as a rare, tangible link to other star systems and a vivid reminder of how much about our cosmic neighborhood remains to be discovered. For thousands of years, humanity looked at the sky and saw stars as distant, unchanging, unreachable points of light. Even after we developed telescopes, after we figured out that they were distant suns like our own, after we discovered that they host their own planetary systems, the stars remained fundamentally separate from us. Interstellar space seemed like an impenetrable barrier,
an ocean so vast that nothing could cross it. But 3I Atlas proves otherwise. Objects do travel between the stars. Comets born around distant suns can and do make the journey across the interstellar medium, surviving billions of years in the harsh radiation environment of deep space, maintaining their volatile ices locked in cold storage, traveling at tremendous velocities through the cosmic void. When they arrive at our solar system, they bring with them a message from worlds we will never see, carrying chemical fingerprints of alien protoplanetary disks of formation processes that occurred before our own sun ignited. Every measurement of 3I Atlas, every spectrum, every polarimetry curve, every image, is a sentence in that message, and we're only beginning to read it. The discovery of 3I Atlas raises questions that will occupy astronomers and astrobiologists for decades to come. How many interstellar comets have passed through our solar system undetected before we developed the survey technology to catch them? How many are passing through even now on trajectories that take them far from the sun, never to be spotted by our telescopes? The void between the stars is not empty. It's filled with wanderers, with refugees from dead planetary systems, with the debris of stellar nurseries long since dispersed. We've caught only the barest glimpse of this cosmic menagerie. More profoundly, 3I Atlas challenges our assumptions about life and chemistry in the universe. The complex organic compounds detected in its coma, the carbon-rich chemistry, the porous dust grains, these are the building blocks of life as we understand it. If such molecules can be preserved during billions of years of interstellar travel, if they can remain viable despite exposure to cosmic rays and the harsh vacuum of space, then the chemical ingredients for biology may be more widespread in the universe than we ever imagined. An interstellar comet could be a delivery mechanism carrying the seeds of chemistry across the gulfs between stars. This doesn't mean 3I Atlas is biological. It's not. The data make that clear. But it does mean that the pathways for chemistry to become increasingly complex, for the simple to become the sophisticated, may exist throughout the galaxy in ways we're only beginning to understand. Every comet that falls from interstellar space to a planetary system brings with it this potential, this possibility, this hint of a universe far more chemically interconnected than our theories have previously suggested.
Despite all the data we've gathered, despite the spectacular images from Hubble and JWST, despite the careful spectroscopy and the polarimetry measurements, 3I Atlas remains fundamentally mysterious in many critical ways. This is not a failure of science. It's the normal state of science when confronting something genuinely new. Uncertainty is not the opposite of knowledge. Uncertainty is the foundation upon which knowledge is built. Consider the question of rotation. Those ground-based observations hinting at a possible 16-hour rotation period, they remain inconclusive, buried under the glare of the coma, masked by the dust and gas pouring from the surface. We don't actually know how fast this comet is spinning, or even whether it spins in a simple way or tumbles in a complex, chaotic pattern like a mualua. And that matters. Rotation affects how ices sublimate, how dust is ejected, how the coma develops.
Not knowing the rotation period means missing a crucial piece of the puzzle. Then there's the composition of the nucleus itself. We know the overall size constraints, but what is the nucleus actually made of? Is it primarily water ice mixed with rocky material, as most solar system comets appear to be? Or is it something different, something shaped by the colder, more carbon-rich environment of its formation? We have hints from the gas and dust in the coma, the dominance of CO and CO2, the unusual dust properties, but these tell us about what's being shed, not necessarily about the composition of the nucleus itself. Different ices have different sublimation temperatures. Different materials have different densities. The internal structure could vary dramatically depending on what we find when the comet is studied more carefully. The outburst activity remains another open question. The sunward dust plumes, the violent jets of gas, the sudden flares, these suggest a nucleus with a heterogeneous structure, with pockets of highly volatile material close to the surface. But where exactly are these pockets? How deep do they extend? Are they scattered across the nucleus or concentrated in specific regions? The polarimetry data suggests the dust is uniform across the coma, hinting at a global process. But that could mean the nucleus is uniformly active, or that we're simply not resolving the regional variations. The data haven't yet provided a definitive answer. Most intriguingly, there remains the question of what happens at perihelion. All the observations made so far have been from a distance, with the comet still relatively far from the sun's intense heat. When it reaches its closest approach, when solar heating reaches its maximum, what will happen? Will new spectral features emerge? Will outbursts occur? Will fragments break free from the nucleus? Will the comet survive intact or disintegrate? Every scenario is possible. The data we have constrain the possibilities, but don't eliminate uncertainty. Only time and the observations made during and after the perihelion passage will reveal the truth.
What makes 3I Atlas unique among interstellar objects is not just its properties, but the scale of the observational campaign mounted to study it. When Oumuamua arrived in 2017, survey telescopes had just barely caught it, and it was already slipping away, moving faster than most comets, beyond the reach of detailed investigation. By the time astronomers realized its significance, it was too late for a comprehensive study. The comet escaped before we could truly understand it. Borisov arrived in 2019 with more warning, and telescopes around the world gathered data. But the campaign was still somewhat improvised, reactive, conducted on a scale limited by existing observing schedules and available telescope time. Astronomers made the best use of available resources, but they were always playing catch-up, always working to fit their observations into a crowded observing schedule. 3I Atlas is different. This is the first interstellar object to be caught early enough for a truly comprehensive, planned, global scientific campaign. Major observatories have rescheduled their normal programs to accommodate the study. Hubble has allocated precious mission time. JWST, one of the most sought-after telescopes in the world, has devoted multiple observation sessions. Ground-based facilities from Gemini to the Very Large Telescope to the Nordic Optical Telescope have all made space in their schedules. Amateur astronomers from around the world are conducting observations and sharing them through online networks. Citizen scientists are contributing data that professional astronomers use in their analyses. This is science at its best: coordinated, collaborative, leveraging every available resource to maximize understanding of a phenomenon that comes once in a lifetime. The data will be archived, made publicly available, analyzed and reanalyzed for decades to come. Students decades from now will write dissertations on 3I Atlas. Researchers will discover new patterns in the data that were overlooked in the initial rush. The full scientific return from this discovery will continue to grow long after the comet has disappeared into the interstellar dark. The coordination extends beyond Earth as well. Space missions in orbit, SOHO watching from the Sun's perspective, TESS monitoring from its survey orbit, MAVEN tracking from Mars, and others all contribute pieces to the puzzle. The combined data set, when fully analyzed, will be enormous. Thousands of spectra, millions of images, detailed measurements of every accessible property of the comet. It's a level of intensity usually reserved for nearby stars, for exoplanet discoveries, for objects of intense ongoing scientific interest. An interstellar comet is receiving that treatment.
What 3I Barbie Atlas teaches us extends far beyond the specific properties of this particular comet. It forces us to rethink fundamental assumptions about our solar system and its place in the galaxy. First, the solar system is not isolated. It's not a hermetically sealed system developing in splendid isolation from the rest of the galaxy. Rather, it's embedded in a galactic context, constantly subject to influences from outside. Interstellar objects pass through regularly, though we've only recently developed the technology to detect them. The frequency with which such objects arrive is still uncertain, but even if it's rare on a human timescale, it's essentially inevitable on an astronomical timescale. Over billions of years, countless such visitors have arrived, each carrying material and potentially delivering it to our planetary system. Second, the diversity of comets is far greater than we had appreciated. By studying only the comets native to our own solar system, we were seeing just one slice of the full spectrum of possibilities. Interstellar comets expand that spectrum, showing us that comets with radically different compositions, formed under radically different conditions, are possible and real. This means our models of cometary physics, developed from decades of study of our own comets, need refinement and expansion to encompass this broader diversity. Third, the delivery of complex organic material to planets may be more efficient and more widespread than we previously thought. if interstellar comets regularly pass through planetary systems, and if they carry the kind of organic-rich material that we're detecting in 3I Barbie Atlas's coma, then there is a mechanism for spreading the chemical building blocks of life throughout the galaxy. Not life itself, but the chemistry that life requires. This has profound implications for the search for extraterrestrial life. If the ingredients are common, if they're being delivered to planetary systems around distant stars, then the path from chemistry to biology may be a well-worn one. Fourth, the study of interstellar objects provides a window into exoplanetary systems we can never visit directly. When 3I Barbie Atlas arrives in our solar system, it brings with it a sample of another stellar neighborhood, a physical specimen of material that originated light years away. By studying it in detail, we're conducting an indirect investigation of a distant planetary system. It's like having a messenger arrive from a foreign land, carrying goods that tell us about that distant place. Every spectrum is a word in that message. Every image is a picture of a world we'll never see, but can partially understand through the proxy of the visitor.
3I/Atlas will not be the last interstellar object to visit our solar system. Astronomical projections suggest that similar objects should pass through our planetary system roughly once per year, though most will be faint and easily missed. Now that we know what to look for, now that we've developed survey strategies and automated detection systems, we should catch more of them. Over the next decade, we might expect to discover dozens of interstellar objects. Over the next century, hundreds. Each one will tell its own story, will reveal different aspects of the interstellar population, will expand our understanding of the galactic context in which our solar system exists. Some of these future visitors will resemble 3I/Atlas, active comets with complex chemistry, telling stories of formation in cold, alien environments. Others will be more like Borisov, familiar, predictable comets that might have been born in our own Oort cloud if the circumstances had been slightly different. Still, others might resemble Oumuamua, enigmatic, difficult to categorize, following rules we don't yet understand. The full diversity of interstellar objects remains to be explored. The survey technology will improve as well. Better telescopes, more sensitive detectors, faster data analysis, artificial intelligence algorithms designed to pick out moving objects in the noise. All of these will make future discoveries easier and will catch fainter objects that we currently have no way to detect. What looks like a complete discovery now, 3I/Atlas, the bright, dramatic, easily detected interstellar comet, might look in hindsight like just the tip of an iceberg. The truly faint population of interstellar objects might dwarf what we've seen so far. And as more data accumulates, as more interstellar objects are studied, patterns will emerge. Statistically significant trends in composition, in size distribution, in orbital characteristics. These patterns will constrain models of planetary system formation and evolution around other stars. They'll tell us about the processes that eject material from exoplanetary systems, about the densities and compositions of material in the galaxy, about the prevalence of habitable environments and the delivery mechanisms of potential biosignatures.
3I Atlas arrived at a particular moment in human history. We have the technology to detect it. We have the intellectual framework to understand what we're seeing. We have the global infrastructure to coordinate observations across the planet and beyond. We have the mathematical and computational tools to analyze the data and extract meaning from it. 1,000 years ago, 1,000 years from now, this comet would have meant nothing to us. It would have passed through our solar system undetected and unmourned. But now, at this moment in time, this visitor from the stars has become a teaching tool, a mirror reflecting back to us how much we've learned and how much remains mysterious. The data gathered on 3I Atlas will be studied for decades. Papers will be published, conferences will be held, hypotheses will be formed and tested. The comet will teach us things we didn't anticipate learning when it first appeared on our telescopes. Years from now, when new interstellar objects arrive, we'll understand them better because of what 3I Atlas taught us. The study of this single comet will advance the broader field of cometary science, reshape our understanding of the solar system, and expand our perspective on our place in the galaxy. More profoundly, 3I Atlas reminds us that science is an ongoing conversation between humans and the universe. We ask questions through our observations and experiments. The universe answers through the data we collect. We interpret those answers, formulate new questions, and ask them again. 3I Atlas is part of that conversation, a voice from the stars speaking to us in the language of physics and chemistry, telling us about worlds we'll never visit, about conditions we've never experienced, about the true scale and diversity of the cosmos.
As October moves toward November, as the date of perihelion approaches, the intensity of the observational campaign will only increase. Every available telescope will be aimed at 3I/Atlas in the days before solar glare renders ground-based observations impossible. Scientists will be racing to collect as much data as possible before the comet disappears into the sun's glare. Spectra will be taken rapidly, images captured in succession, any unusual activity documented with precision. It will be a frenzy of observation, a concentrated effort to capture every bit of information possible before the blackout period begins. Then will come the waiting. For weeks, ground-based observers will be blind, forced to rely on space-based telescopes and hope that they're positioned correctly, that their instruments function properly, that something truly remarkable doesn't happen without being recorded. There will be tension, anxiety, the worry that some crucial observation will be missed. It's the hardest part of astronomy, having to wait, having to trust that your planning was adequate, having to watch the calendar knowing that you can't intervene if something goes wrong. But then, in early December, the comet will reappear. The sun's glare will diminish enough that ground-based observers can see it again, and the observations will resume. There will be a hunger to compare the pre-perihelion observations to the post-perihelion data, to see how the comet has changed, what new features have emerged, how the extreme solar heating has altered this visitor from the stars. The data will flow in again, fresh measurements, new insights, confirmation of predictions, or surprises that force models to be revised. And through it all, 3I/Atlas will continue on its trajectory, following the orbit that it's been on for billions of years, unaware of the attention it's receiving, indifferent to the questions we're asking about it. The comet will have its closest approach, will feel the most intense heat it's experienced since leaving its parent star, will make its closest approach to Earth on November 12, 2025. And then it will begin to recede, moving outward, accelerating away from the sun, heading back toward the interstellar dark from which it came. In a few years, as its distance grows and its brightness fades, the observations will dwindle. Fewer and fewer telescopes will be pointed at it. The flurry of papers and discoveries will slow, then stop. The comet will return to being just another faint, distant object, interesting only to specialists. And eventually, it will slip below the detection threshold of even our most powerful telescopes, receding into the infinity of space, becoming once again just a small, cold chunk of ice hurtling through the void. But the data will remain. The thousands of spectra, the millions of images, the careful measurements and the mathematical models, all of it will be archived and preserved. Future astronomers with better technology and deeper insights will return to the data from 3I/Atlas and extract new meaning. They'll see patterns we missed. They'll understand phenomena we merely documented. The comet will continue to teach us long after it's gone, a voice from another star system continuing to speak to us across the vast distances of space and time.
3I/Atlas is more than just a comet. It's a messenger, a physical link to worlds we'll never visit, carrying a message written in molecules and dust grains, in spectra and light curves, in all the intricate details of its composition and behavior. The message is complex and still only partially decoded, but its central theme is clear. The universe is far more diverse and interconnected than our local experience might suggest. We are not isolated. Our solar system is not unique. The chemical building blocks that make life possible are not confined to our corner of the galaxy, but are distributed throughout the cosmos, carried on the backs of wandering comets, spread across the void between the stars. The story of 3I/Atlas is the story of that interconnectedness, of how distant worlds speak to us if we listen carefully enough, if we build the right instruments and ask the right questions. The real knowledge about 3I/Atlas is stranger and more uncertain than the hype surrounding its discovery. But it's also more profound, more meaningful, and far more beautiful. In the cold darkness of space, in a nucleus of ice and rock no larger than a city, in the dust and gas streaming from its surface, in the chemical signatures we decode from billions of kilometers away, there is a tale of the universe's true scale and mystery. It's a reminder that we live in an age of discovery, where the sky still holds secrets, where visitors from other worlds still arrive to teach us about the cosmos, where science still has the power to astound and humble us. 3I/Atlas will pass through our solar system this once, its existence a fleeting moment in cosmic time. But the questions it raises, the data it provides, the understanding it offers, these will endure. This comet from another star has given us a gift, a window into the universe beyond our own, and a reminder that the cosmos is far stranger, far more wonderful, and far more interconnected than we ever imagined.